recent stuff we got into was this idea of similar matrices. And it's really unfortunate we're just not going to have enough time to really dive into all the ways that they're similar. But I did put on this sheet, I want to point out, Jeff, you're writing on it. Down here, wait, where is it? Shoot. Wait, glasses. Where did I put it? Don't worry about it, Jeff, it's on here somewhere. Oh, here we go. Yeah, thank you. This is exactly what I'm looking for. I thought I had put it as a bullet list, but no, I just put it in one big thing. So two similar matrices share the following properties, yes? Mm-hmm. So if I know they're similar, they have the same eigenvalues, the same trace, the same determinant, the same rank. If they're not similar, if they are similar, they don't share these properties. Which kind of makes sense. Similar is basically, it's a matrix that somehow operates the same way, but on different bases for your space you're working in. So it kind of makes sense they should share certain things, but others no. Eigenvectors make sense because now they're based on different bases, so they're not going to look the same. Which means all the four fundamental subspaces have to be different also, because you're going to get different column space, you're going to get different blah, 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 blah. Does that make any sense? So I've kind of taken a similar matrix is one that is shifted somehow according to the, related to the first one, but they do sort of the same thing. What's really neat, and this is where you want to try to get, is you can get to a point where you have a matrix, and what it does is it takes your vector and it kind of rotates it around this way, and it makes it longer, and then it moves it this way, and it does all these weird things to it. If you find the right basis, it will only ever make it longer or shorter along a certain basis direction. Are you guys all with me? It's really kind of nifty. That's some kick-ass shit. That's the ultimate basis set of basis vectors you can get. And not surprisingly, they are based on eigenvalues and their eigenvectors. Yes? Okay. Whew, that was a long way to say all that. I wanted to see also if I put no. It's okay, Jeff. All right, so let's do this. Let's do something that's going to help us later. I like that idea, Jeff. Yeah, here we go. Where did I do this problem? I can't remember. Oh, here we go. Sorry, I'm trying to remember how much I've already told you guys. Yeah, okay. That's where we ended up. Perfect, so we're right here. So let me make something very clear. Let's see how much you guys can go with me on. Let's say A is this. How do I find the eigenvalues and the eigenvectors? So what determinant can I set up? I can go straight to a determinant, right? 2 minus lambda, yeah, exactly. So a minus lambda I love it. So in practice, that'll be this business here. Is everybody cool with what's happening? Okay. You're all like, I guess so. I signed up for it. Now, real quick, can you guys, all right, let's try to do this by hand. Yes, in fact, your calculator couldn't do this for you because it's got a freaking lambda in the shit. You can't put that in there. So what's at least semi-nice about this? If we got to figure out the determinant, which row or column would you use? First row or the last column? Yes, because they have the 0 in the corner. Yes. Can everybody just take 2 minutes? Pick one of those. Figure out the determinant. I already did it, so I'll tell you. I'll tell you what it is here. But try to do it. Let's see. Because you know I'm going to make you do this. Well, you have to do this by hand. I'm not going to give you a 3x3 that's got like a crazy amount of work. I'm not going to give you a 7x7 matrix with no zeros. That would be insane. You would be allowed to come up and kick me. Everybody, that would accumulate to a lot of pain. So I'm not going to do that. You guys can check me. So I think probably most of you guys are doing it around the first row. So just to kind of show the work fully. Where am I at? Yeah. Now, I want to show you something. How many guys did this? How many guys did the first row? That's what I did too. If you did the other column, I don't know what the hell's going to happen to you. So let's see if something similar happens. Right here, has anyone gotten this that did it this way? No? Okay, sorry. You're like, back off, dude. So I'm going to put what I got. Did anyone get it? Lambda squared minus lambda minus 3. Yeah. That looks gross. Yes? Is that factorable? I'm okay about it though, because I'm not done yet. So I get minus 1 times, this one comes out nice. Lambda minus 2. I love it. Now real quick, I'm going to do this. Ooh, look at Jeff go. So, dear God, please, dear God, or whatever the hell, deity, God of coffee, the flying spaghetti monster, whatever works. Do not multiply that shit out. Yeah? Because what's the whole point? What's the thing I'm supposed to be doing next? Factor. And so what do I notice here? Do you guys see what I mean? Do not multiply that shit out. Holy shit. What can I take out? What comes out? 2 minus lambda. What's left? What do you mean minus 2? What?
Minus 3 plus 1.
Oh, I see what you mean. Gotcha. Yes, the next step will be minus 2. So now I can do what with this? I'll tell you what to do with that. I don't want it equal 0, right? Because that's the whole idea, is I'm trying to make this singular so I can get the null space. Finding eigenvalues and eigenvectors is effectively finding the null space of A minus lambda I. And of course I can factor that next dude down, right? So let me say something you probably haven't heard. I'm going to divide by -1. Is that cool? I don't care if it is. I did. There's a word multiplicity. Does anyone remember multiplicity? There's a movie with Michael Keaton. It's a really good one. It's called Multiplicity, so I would highly recommend it. But you don't have to watch it. What do I bring up multiplicity right now? What's the multiplicity of -1 as a root? 1, because it shows up once. What's the multiplicity of 2? 2, because it shows up twice. I love it. That's going to become big here in a minute. Lambda equals 2, multiplicity 2. Lambda equals -1, multiplicity 1. Now it's just coincidence that 2 goes with 2, blah, blah, blah. Be careful. Okay. Have you guys, you probably haven't, take a moment and figure out the eigenvectors, or at least start to set it up. This gets a little bit worse. So this one I would probably let you do something. I'd probably let you use your calculator so you're not spending all day row reducing this thing. So what I mean is, if lambda equals 2, what does the A minus lambda I matrix become?
0, 1, 0, -1.
Yeah, 0, 1, 0, -1, -2, 1, 1, 3,
-1.
-1. Kick ass. Yeah, is that what you got past Jeff? Oh, you're looking at the wrong one. I was like, past Jeff really screwed up. Nope, that's the one. Okay, good. Now, if you throw that in your calculator and row reduce, RREF, then I believe you get, why didn't you finish that out, Jeff? 1, 0, Fudgerama. 1, 0, -1, and 0, 1, 0, yes? Somebody check me out on that. You never know. I'm trying to work out the last couple steps in my head here. I think that's right. Yeah. You guys, so really good thing is, does everybody know how to do row reduce echelon form in your calculator? I know we haven't done a lot this semester because I like to do stuff by hand because I'm crazy. So I'm gonna make you do it because I can't. Ha ha ha. Sorry. But on the final, I will tell you, feel free to use your calculator to do this because it's just gonna be busy work if I make you do that. Yes. Okay. Is that what you guys got? Anybody? Validation. Okay. So can somebody tell? I don't know what you guys have to do to figure it out, but can you see what the
1, 0, 1.
Yeah. So you get 1, 0, 1. That is the eigenvector that goes with what? Yeah, lambda equals 2 goes with this eigenvector. The eigenspace for lambda equals 2 is every multiple of 1, 0, 1. So the eigenspace in this case is a line. There's a problem that we're going to see later, why it becomes a problem. What was the multiplicity of 2? 2. But I only got one basis vector, correct, for its eigenspace? That's a problem. That's not a huge problem. This still works. If I operate on 1, 0, 1 with the original matrix, what will I get? Can somebody just tell me what I'm going to get? No? No? What does 1, 0, 1 go with? What value? 2. So if I operate on 1, 0, 1 with my original matrix, what will I get? 2, 0, 2. That's what we just discovered. If my vector is this, or on this line, every multiple of this, and I operate on it with the matrix, I'm going to get twice it. So if I operate with 5, 0, 5, what will my answer do? 10, 0, 10, because 5, 0, 5 lies in this guy's direction, yes? Now, also, we're not done yet, because we have the whole other eigenvalue, yes? But let me just keep going. And you're like, yes, what you do, Jim? Did I get lambda equals 0 as one of my eigenvalues?
Yeah.
Did I?
No. Yeah.
Did I get lambda equals 0?
Yeah.
No. So, I really want to tie this up in a bow. Remember how last time we operated with a vector that was close to an eigenvector? And it snapped onto the line of eigenvectors? I don't know if you guys remember this. That only directly works if you actually get lambda equals 0. There's not time for me to get into this, but just when you operate with the matrix, both eigenvalues end up contributing to your answer. The more aligned it is to either eigenvector, the more in that line, the more that one's going to dominate. The larger eigenvalue ends up dominating in the end. So if I operate on 1, 2, -1, that might be too far away. 2, 0, 3. Over and over and over again, it is eventually going to line up with 1, 0, 1. In the interim, the other eigenvalue kind of contributes to the answers. That's why it's off. That's why if lambda equals 0 was the other eigenvalue, it's perfect. Because lambda equals 0 contributes 0. So it snapped right into place. I have no idea if you guys remember this. It was such a cool thing. Our eigenvalue was 1, 4. We operated on 1, 3. We ended up with a multiple of 1, 4. So it snapped onto the 1, 4 line. Okay. That snapping is huge. Huge in the applications of linear algebra. Okay. Whew. Now, just to cut to the chase, is everybody, do you guys, you need to understand that because I'm gonna let you do this row reduced echelon form business and not make you do the whole reduction, this kind of problem is just beautiful. It's like, give me this, because it's just algebra. It's just algebra. And then you throw shit in your calculator and you sit back. Okay. So too bad, I'm not gonna give you a bunch of these, huh? This one, if you do all the work, oh my God, Jeff. You can you end up with, here we go. I think you get this. You actually get like 1/4, -3/4 1, but then you can kind of normalize it a bit. So the eigenspace for lambda equals 2 is 1, 0, 1 times t. And the eigenspace for lambda equal -1 is 1, -3/4 times w, or whatever multiple you want to use. So everybody with me? An eigenspace only exists for a specific eigenvalue. How big do you think the eigenspace for lambda equals 2, how big do you think it should be? 2, because there are multiplicity of 2. In order to do something we're about to get into, it should be 2. Okay. Blah, 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 blah. Blah, 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 blah. Yeah, okay, good. Okay, good, good. So that was one thing from there. Coming back into similar matrices. The whole idea with a similar matrix is if I can write this, if I can find a C so that A and B are connected by this equation, they are similar. And then you have that whole list of things that stay the same. They have the same eigenvalues, so forth, yes? Same rank, same determinant, same blah, 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 blah. That seems highly useful, especially if B is way nicer than A, or A is way nicer than B, or we talked about the fact that if you can take a matrix and factor it like this, who remembers how I would do, well, that is if, be careful, Jeff, if we actually have, how do I want to write this so it's more like what we were doing? Here we go. I'm going to be very specific here, eventually, here. All right. Do you remember if I solve for A, I get C, B, C inverse? These are two arbitrary matrices. In fact, the very first example we did of this, I chose a matrix, and then I chose a matrix C, and then we built B. We didn't start with A and B. We constructed B out of nothing, yes? In general, what you do is you start with a matrix, and then, this isn't in general, but most of the time we're going to do this, there are multiple ways to do this. There are potentially multiple C's that go with multiple A's that make B. So there's often more than one way to factor B like this. Are you guys at all with me? So then you have multiple similar matrices to B potentially. This specifically is when we have the eigenvalues and eigenvectors. And this we did one example of. C would be the eigenvectors, and let me call them, for want of a better, what are you going to call them, Jeff? It doesn't matter, dude. Let's call them, I don't want to call them E. I'm going to call them D, sure. No, don't call them D because you got a matrix D, Jeff. I'm going to call them W, sure. So W1, W2 are eigenvectors. So I put the eigenvectors in as columns. I don't know if anybody remembers we did this. And I put into D, I put the eigenvalues that go with those vectors. So lambda 1 goes with W1, lambda 2 goes with W2. If I do that specifically, not only am I guaranteed, so A is the given matrix, C is the matrix I get if I put the eigenvectors in. D is the matrix I get if I put just the eigenvalues going down the diagonal, yes? then C inverse will be A. And then what is one really nice property of this? Does anyone remember one really nice property of this? If all this stuff is how it went into this, what is A to the 78th power?
C D to the 78th, C inverse.
Yes, and we basically proved it. It was a really quick proof. You just square it, and then once you see what squaring does, you get all the powers. But you just keep doing that until you get to where you want to be. And D is a kick-ass matrix, right? It's not upper or lower, it's just diagonal. That's one reason why we chose the letter D. We're pretty good at that sometimes. So that is one little immediate nice thing about this is, if I have a program that has to do this kind of thing a billion times, I'd much rather take a matrix, factor it, bam, 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 I can get all these different powers. Efficiently, quickly, less computation time. Okay.
For any powers, you.
I'm sorry. Yeah, I'm sorry. There we go. It's for any power, yeah. Because the way it's built, A squared, you see how it condenses, and then A cubed would do the same thing. Every power. One thing we're not going to talk about in this class is, like, what does A squared mean? That seems dumb, but A times A. It shouldn't be an immediate thing, because matrices are a different thing than numbers. So they don't have to act. In fact, we know they're not commutative in general, for example, right? So, I don't know why, but what would A to the 1/4 be? All right, let's not do it. Okay. I just want to throw that out there. So, even your 284 is just the tip of the iceberg. Yes? And you're like, every class you've ever taken has been tips of freaking icebergs, and I'm sorry. That's what we do here. Okay. How we all feeling there? Semi-decent? Semi-decent. So, the question now is, let's tie this into what we did at the beginning. This process is called diagonalization. Diagonalization. And again, we're really creative. Oh, it's a diagonalization. So the question becomes, when can I do this? And considering how C and D are constructed, when do you think you can do it? And I kind of built us up to that. Didn't we just do a problem where I said there's an issue here for a certain reason?
Yeah, maybe when you have all the eigenvalues and eigenvectors.
If the multiplicity, so that's the algebraic multiplicity of your eigenvalues, matches the, I think the book calls it geometric, but just the number of eigenvectors, yes? And then you would have, these would be the right size to create A. You wouldn't have any zeros anywhere and so forth, yes? Actually, zeros would still work, believe it or not. If I get a lambda 0, it still works. I think I have an example like that. So, real quick, let me see if I can sum this up. And I can't remember if I put this note somewhere on that sheet. But I am able to diagonalize a matrix when either, if it's n by n, I actually get n distinct eigenvectors, or the multiplicity of an eigenvalue matches the number of eigenvectors that goes with it. So, a quick example of a matrix that works. That would be nice, Jeff. What's a matrix that actually works? Here we go. Without doing all the work. This movie stinks. All right. Sorry. Because I believe you all do not need to see this over and over. If I do all the work on this thing that we did earlier, I end up with these eigenvalues. Oh, Jeff, lambda 3. Because lambda 1 and lambda 2 are the same. It doesn't matter, Jeff. Negative 2. Okay. We'll do this. There we go. So lambda equal 1 has a multiplicity of 2. Lambda of negative 2 has a multiplicity of 1. I don't know if you guys can decode what I've written up there. I should have just left it without little subscripts, but too bad. Okay. Multiplicity 2 means the two lambdas are the same. And can somebody tell me, what the determinant of this must be?
Lambda minus 1 equals 0 times lambda plus 2 equals 0. But lambda minus 1 squared.
Yeah, -2. Sorry, Zach. If you just multiply the eigenvectors, then you'll get the determinant of your matrix. What should the trace of the matrix be? Which should be the sum of all the pivots.
0.
Yeah, because you just add up your eigenvalues. So it'd be 1 plus 1 minus 2. Yeah, okay. You guys all with me? Sort of? Pretty sure I put that down there. Okay. All right, that was all side notes, sorry. If I find the eigenvectors, I actually get 2 for this one. And for this one, I get 1.
Yay.
Is A diagonalizable? Diagonalizable. Yes, because the algebraic multiplicity matched up with what's called the geometric multiplicity, which is just the number of freaking vectors I got for the eigenvalue. Yes. It would make a full C and D. They would multiply to get your A the right way. You guys kind of with me? Yes.
If you have multiplicity like 2 and you only have one eigenvector, is there only one eigenvector that exists?
Yes.
Okay.
Unless you decided not to find the complex ones. You know what I mean? That's the only way, yeah. If you've done everything correctly, there's no like hidden eigenvector that you have to do something special. You have to actually come in and say, yeah, I want the off the menu, right? No. It's got to be on the menu. Yeah. Okay. How we all? You guys all right? So let me see. Could you guys, without, we're not going to multiply this shit together. Could you set up C and D from this? Could you set up C and D? Where's the example we did? I don't know. It's not that one. No. So if I just start populating straight across, what must go here and here?
1.
Yeah, 1, 1, and what goes down here?
2.
-2. Good. 0, 0, 0, 0, 0, 0. So then you can do your C inverse and blah 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 blah. Yes. Blah 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 blah. Okay, how are we feeling about that? That I might put some notes on the test if I ask you to do one of these, just because that process is a little convoluted and we haven't really played with it that much. So that one I could be talked into putting some instructions on the fly. You guys understand what I'm saying? Okay. Every now and again, Jeff. Blah blah blah. So, blah blah. Yeah, that earlier one, the earlier one that we got with the multiplicities didn't match. That's not diagonizable. Agonizing. Yeah. Okay. Here's something. I don't know if I've written this down yet. Let me see. Here we go. I think this is on your sheet. In fact, I'm just going to point it out on the sheet. It's right here, Jeff. Right down here. A is orthogonally diable if there exists an orthogonal matrix Q where A equals Q inverse DQ. So that has the same format, but now the C matrix that we would put together is actually made up of orthogonal matrices. So eigenvectors don't have to be orthogonal to each other, yes? If they happen to be, then that we call A orthogonally, you can do it, Jeff, diagonalizable. I feel like freaking Harry Potter. Okay. Diagonally. Oops. All right. It sucks that I can't. Anyway. Authors and doing stupid shit. That's okay. And then number 9 is, did I point this out one already? Yeah. If these three are equivalent. If I know one of them, that means the other two are true. So if I know A is symmetric, then A is orthogonally diagonalizable. I said this word earlier, fine. Diagonalizable. There we go, thank you. And also A has a set of orthonormal eigenvectors, which is kind of a big step there, yeah? Because what's orthonormal? Yeah, unit orthogonal vectors, yeah, cool. Okay, well, it's kind of silly. If I know that they're orthogonal, I can just divide by their frequent lengths to make them orthonormal, which is what we do. Okay. Yes?
Isn't an orthogonal matrix, doesn't it have orthonormal columns?
Do it again, sorry?
Doesn't an orthogonal matrix have orthonormal columns?
No, it could just have orthogonal columns.
Huh. I thought that was weird, but I thought like in the homework it was saying that orthogonal matrices had orthonormal columns.
No. Here, real quick, let's see. You never know with our beautiful author. Sorry, everybody. I want to make sure. Wait a minute. Let me think. That was from chapter 4 yet? No. Wasn't it a while back we talked about orthogonality? Orthonormal?
The end of 4 or beginning of 5.
Yeah. Here, orthonormal bases. So when he talks about if a matrix is, the columns are orthonormal if this. He does say orthogonal matrix. That's not right. I love you. Let's see. There is a distinction between a matrix whose vectors are perpendicular to each other versus a matrix that's made up of also ones that are unit length.
So like
So it sounds like Strang just doesn't really make that distinction. So you do it
the book is wrong and like there's a difference between orthogonal matrix and
Yeah,
orthogonal.
there is.
Okay.
It's weird.
That is weird.
I didn't pick up on that. Okay. I don't know if he makes a distinction. All right, sorry. That's a side note. I gotta look that up. See what he says. How do we feel? So the orthogonal and the orthonormal stuff, I feel like we sort of went through that a little bit quickly, but we'll see. Where do we get orthogonal or orthonormal vectors from normally? No pun intended.
Gram-Schmidt.
Yeah, Gram-Schmidt. Yeah.
Yes, maybe he just assumed that by doing the process, you'd also divide by the length, and then
Yeah, but he actually, it looks like he defines orthogonal matrix to have orthonormal vectors, orthonormal column vectors, which, anyway, I'm sorry, don't worry about it. We know there's a distinction. There's an obvious distinction. Okay. Let's see, where did I leave off? Okay. All right, let me make sure I didn't miss anything. No. Oh, real quick. So if I give you this matrix, okay. First time my eyes get all fuzzy when I try to look at it. Not just because I need glasses, but it's just weird with all negative ones and ones. What kind of matrix is that? Symmetric. Okay, wait. And what do we know about it? It's see, you try to say it. Orthogonally diagonalizable. Okay. Sure. Fun with words, kids. All right. So that means that if I wanted to, if I actually go through the process of finding the eigenvectors for this and constructing and the eigenvalues and getting D and getting C, the C will actually be orthogonal, but I do have to make them orthonormal. I do have to divide by their lengths. So just, I don't know if you guys, no, we don't have time. We already did enough of this. Just to cut to the chase, if I would get these eigenvalues. I'll just stick with this, sure. And I really want to make sure you guys understand what this means. If I operate with this matrix on this, what do I get? If I operate with this matrix on this, what do I get? Negative 2, 0, 2. What do I get if I operate over this? Negative 2, 2, 0. Yeah. So either one of these ends up doubling the result. Now, an interesting question would be, what about a linear combination of these two? So let's try it real quick. Somebody give me a number. Who is it? Zach, you said 3? And I heard somebody in the back go, 4. Okay, so 4. Sorry. So if I take the vectors I just gave you, so this is 3 times v2, and this is 4 times Jeff. v3, I get negative 7, 3, 4. So, real quick. 1, negative 1, negative 1. Negative 1, 1, negative 1. Negative 1, negative 1. If there's going to be a problem, shit. See, right there, where you're going to make a sign mistake, that is the one. So I got to be careful. What happened? If I operate on this, let's see what we get. This is a nice little experiment. I should have asked you for a prediction, but that's okay. So it looks like I get negative 7 minus 3 minus 4. 7 plus 3 minus 4. You could do it, Jeff. 6. And then I get 7 minus 3 is 4 plus 4 is 8. So how does that relate? Times 2. That kicks ass. So that should have been your prediction. So that's kind of neat. That creates, that's why we call it an eigenspace, because every vector in that space will actually react the same way if acted upon by the matrix. That is kind of cool. But one thing that's really easy for students to get wrong is they think eigenspace, just put all the eigenvectors into one matrix. Hell no. The only time you do that is if you're trying to diagonalize your matrix, yes? That's how I construct the C and the D, is the eigenvalues and the eigenvectors. Are you guys at all with me? When I say eigenspace, there's an eigenspace for every eigenvalue. What's the dimension of the eigenspace for lambda equals 2? 2, that's crazy, okay. So, of course, it defines a geometrically plane. So every vector in the plane, that matrix has the same effect. It just doubles it. So then you might start to think, what if I use these as my basis vectors for my space? Because they operate really well with this matrix, and that's kind of like would be the next step of what we're doing. But I don't know if we're gonna make it there. Okay. I think we talked about that. I think. Let me see. Yeah, we did. Just to really hammer this home, I said this earlier, but the determinant of A equals the product of its eigenvalues, yes? I think I put that on that sheet, did I?
Yes.
The trace of A, yeah, I'm pretty sure we talked about this also, is the sum of the eigenvalues. What's the trace itself defined to be? Because the trace can exist for every matrix.
Some of the diagonal values?
Yes. Some of the diagonal parts. Oh, God, okay. I think that's on that paper. Blah, 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 blah. Do I want to do this? No, okay, beautiful. So I will say one thing. I think I want to do one problem with you from the. I think it's section 6.3 is the positive definite matrices. I'm not gonna look. Who cares? Now I gotta make sure. 6.3 was symmetric positive. Okay. So real quick word about 6.3. And everybody's fully aware that that's extra credit, yes? Okay. But just a real quick word about it. All a positive, definite, I love this, by the way. All a positive, definite matrix is one where all of the eigenvalues are positive. Definitely. So, that's it. So what do you think a negative definite matrix is?
Eigenvalues are negative.
Holy shit. What do you think a semi-definite matrix is?
Some are positive, some are negative.
Yes. Okay. So here's the one little thing that I want to focus on from this section. There's a lot in here, but I want to do this one trippy little dude. Can you guys, here, really quick little reminder thing. If I want to do the eigen values of this, just out of nowhere, Jeff. Well, I didn't even do this to see how gross this is. Shoot, let's see how gross it is together. This would be plus 14 minus 36, so minus, I don't know, I lost track. 22? Yes, okay, good. So this is not bad, thank God. Real quick, this is gonna apply to this section 6.3, but I just wanna start with this. Are you guys all cool with what I just did? And then of course I get what eigenvalues. Oh, let me see. If I factor this, I get minus 11 plus 2. Yes? 11 and negative 2. So that would be semi-definite. Yes? Because it's a mixture of positive, negative. Now, don't worry. I'm going to get there. If I do the same thing here, I should have done this before, but that's okay, Jeff. Did I? Oh, I did that one, but not that one. Good job. Let's see, this will be lambda squared minus 22 lambda plus 40 minus 36. So I think plus 40 minus 36, yeah? Ooh, that's gross. Ooh, that's gross. Is that right? Dumb you, Jeff. Let me see. Did I do that right? Let's see. Lambda squared minus 22 lambda plus 40 minus 36. Yes. Man. If I do, all right, not to waste a lot of time, but just to show you, this should not be surprising. You're in 284. Yes? What should you expect some eigenvalues to be? Not just complex, but, I mean, complex, sure, but less than that. Irrational, yes. So if I do, oh my God, I don't want to spend all day on this. That didn't come out the way I thought it would. That's okay, Jeff. What am I, let me see, hold on. That's probably okay. If I do quadratic formula, well, I get negative b plus or minus square root of b squared. What is that? 444? Is that? No, it can't be. 440. Is it 444?
484.
484. Thank you. I didn't add 440 twice. Damn it. Minus 4ac all divided by twice a. Okay. 22 plus or minus square root of 4. I appreciate your patience with me. 68 divided by 2. What is square root of 468 roughly? Do it again. 21.6. Okay. So do you agree with me? If that's 21.6, both of these eigenvalues are positive. 22 minus 21.6 is positive. 22 plus 21.6 is positive. With me. So what kind of matrix is that? The one we started with. Positive definite, yes? And is it symmetric too? Ooh, so it's symmetric, positive, definite. Okay. So, I love you guys' patience with me. Look at that first one real quick. Here's something we've never really kind of done. Look at that. Look at that monster. Multiply that out. The things you guys do. And you guys with me, it's not 2667. It's that same, it's that first one. I just wrote it really close. I'm sorry. It's 2667, yes? I'm sorry. So this will be 2x, right? 2x plus 6y. And then 6x plus 7y. Is that cool? Bam, 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 bam.
Y.
Say again?
26.
Oh, thank you. Yeah. And then I multiply that by xy, and then I'm going to get 2x squared
Plus 6xy.
plus 6xy.
6x.
Yeah. And this is going to be plus, right, because it's all one thing, 6xy plus 7y squared. I get 2x squared plus 12xy plus 7y squared. Do you see how can you see how you could start with this and somehow get there? There's a whole process. And then you can evaluate this matrix. And what we're doing is, if that matrix at the heart of this ends up being positive definite, then this has a global minimum. The function it came from would have a global minimum. Was this matrix positive definite? No. In fact, it was semi-definite. It was a mixture. So this is so cool, especially for those of you who are or have taken 281. There would be a saddle point here. Since it's a mixture of negative positive, it would go up in one direction, down the other direction. That's the saddle. Saddle point. Some of you guys have never taken 281. I'm very sorry. You're missing out. Yes? Oh, yeah. So it's exactly, it goes up like that and down on the sides. Yes? So that's the saddle. So it's not a minimum or a maximum. It's like this one way and this the other way. It's like I'm not a minimum maximum. It depends on which way you're looking. That's really quick. But I at least want to give it a little taste of what that kind of gets into. It's a beautiful intersection of calculus and linear algebra, and that's as much as I'm going to talk about it. I'm sorry. So if you want to try out that section, you'll be doing that. You'll be getting deeper into some definition stuff, and there will be eigenvalues obviously happening. Okay. So. Oh, good, that's done. Okay. Blah, 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 blah. So now, yes. What's up, sorry? Oh, you asked me a question?
Yeah, are we doing debate on this?
Yes. All right, I have decided to, oh shit, I forgot. Oh well, it's too bad. My camera might die, it's okay. Poor little guy. Does what he can. Oh, that's right. That's okay. The funny thing about these two sections in chapter 8.1, 8.2, I'm pretty sure I already told you guys 8.3 was going to be extra credit. Right? Did I already say that?
Yeah.
I thought for sure yeah. Okay. So we're doing 8.1 and 8.2. Good Lord, in 20 minutes, Jeff. Good job, buddy. The nice thing with this is there's not a lot. Let me ask you, if I tell you we're working with a linear transformation, first off, what the hell is a transformation? Anytime I operate on a vector with a matrix, I'm transforming that vector. For example, a really good, really clear image of this. If I have a projection matrix I've constructed and I operate on a vector with it, don't I transform it into the shadow or into the projection? Yes? So I input a vector and my matrix transforms it into something else. If I have a matrix with an eigenvector that has an eigenvalue of 3, when I operate on a vector, an eigenvector, along that line, I'll get triplet. It transforms it into triplet. It stretches that vector. Yes? eigenvalue 1/2 would compress the vector, blah, blah, blah. Are you guys kind of... So we've been dancing around transforms without ever actually just saying transforms. Some would argue that's the whole reason matrices exist, and those are silly people. Because matrices, you can do a lot more with them. But the funny thing is, every single matrix is a transformation, so I see why they would argue that. So, blah, blah, blah. Let me see where I want to start. So right here, why did I do that? Sorry, I'm disagreeing with my past self. Okay, that's okay, past self. Here's the definition of a linear transformation. And then we'll actually do some examples. That would be amazing. 1, it has to satisfy 2 things. Oh, let me set up some things, sorry. So erase the 1, sorry. Let V and W be real vector spaces. So their components are all real, no imaginary components. Is everybody happy about that? No? I can put some complex in there? No? Okay, most of you guys are like, just do what you're going to do to us. All right, I'm sorry. We say the function, and I want to do this just to show you some of the notation you're going to see. We say the function t that maps v to w. You guys have probably seen that in some form, that kind of notation before. Is a linear transformation if the following is true. For u element of, oh, that's funny, Jeff. Sorry, I just love past me. That's not a bad idea, actually. V element of V and W element of W. There we go. Past me made U element of V. That doesn't make any damn sense. Okay, you ready? Here are the 2 things. If I operate on U plus V with the transform. So just to make sure you really understand, if V is R squared, U could be 1/7. Yes? If V is R squared, U could be 1,7. That vector. You with me? So V and W are these, they could be vectors. What I define as vectors depends. It could be polynomial functions, it could be matrices. We've talked about that before. This would be T of U plus T of V. So this has come up at some point in your math career, this should have come up. There are operations you apply that your instructor should have said something like, this looks linear. Derivatives, taking the derivative. Is it linear? If I take the derivative of the sum, is that the sum of the derivatives? Hell yeah, it's a very fundamental property of derivatives, right? The derivative of x squared plus 5x is the derivative of x squared plus the derivative of 5x, yes? I don't care what functions I've done. Sine of the natural log of 1 over cosecant of 3x is still freaking, still works. Are you guys with me? So you can summarize this to say, if it's a linear transform, it looks like it distributes. Be really freaking careful. This is not t times u plus v. That is t of u plus v. So here's an example of one that's not linear. What about the transform that takes r to r and is defined to be the square root of the input? Is that linear? What's the square root of u plus v? Is that equal to the square root of u plus the square root of v? This is a very simple example of a non-linear transform. Radicals don't distribute across addition or subtraction because they're based on multiplication. Okay. Does anyone have a guess as to what the second thing has to do?
Scalar?
Do it again?
Scalar.
Scalar, yeah. T of Cu must equal C T of U. So a whole class of problems you're going to get in section 8.1 is verify that this transformation is linear. So let's do an example of that. Okay. Let's do a concrete freaking example. Dear God, Jeff. Here we go. This isn't too terrible, I don't think. Let's say that I have a transform that takes r cubed to r cubed. So what it does is, when I feed it, because it's hungry, I'm going to feed it the vector ABC from r cubed. And what comes popping out is this vector. Good Lord, Jeff. If you can't read your own writing, that's fantastic, buddy. I think that's okay. Yeah. Yeah, that'll work. So this is kind of a silly example. How would you verify that that's linear? Do you already have the transform acting on a vector from the input subspace? Or input space, let's say vector space. We try to say it again. Don't you already have what transform does to something? ABC. So you need one more vector. Because what do you have to show? What's the very first thing you have to show? That if I take the transform of a vector plus the transform of another vector, it's the same thing as the transform of the sum of the vectors. Yes? Does that make sense? That's what the first check says. So this, I'm not even going to do it because I'm hoping you guys. So if I do this, what's that? You're never going to believe it. X, y minus z, negative x plus y plus z. So what is t of a, b, c plus t of Jeff? X, y, z. That would just be a plus x. You with me? And do you see how that would be what t of a plus x, b plus y, c plus z? Does anybody not see how that proceeds? I love you guys so much. You're all like, I don't want to say yes. Okay. This would be b minus c plus y minus z, and then I would add these together, blah, 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 blah. What would t of a plus x, b plus y, c plus z, what would that be? That would be the first dude, a plus x. Isn't that what this is? Yes, I'm just following the form, yes?
Yeah.
What's the transform do? It puts the first dude in the first place, everything's great. And then it subtracts the, oh shit, make them fight with each other. So the next one should be b plus y minus c plus z, which is exactly what the shit that is, yes? Okay. Are you guys kind of with me? So I'm not going to give you a ton of those, especially if they're big transforms, because then it just becomes busy work. That's very simple. It kind of reminds me of like, it's even simpler than verifying something as a subspace. Yeah? Do you guys remember doing that? Okay, some of you guys, okay. You guys doing okay? You look roughed up, I'm sorry. Oh, here's some cool shit. Okay. Oh man, do I have enough time to talk about all that? I don't know. What if I have this? I'm gonna do it somehow anyway. Oh, that's right, I do have notes to keep me going. So I want to see if that's linear, this transformation. I want to see if it's linear. Now we're getting into it. So now we've left algebra behind. We've left multivariable calculus behind. And now we're properly in linear, where the transformation is defined through matrix multiplication. So what do I have to show? Well, what's t of u? Where u is an element of r squared, yes? What's t of u? Yeah. So it would be cosine theta, negative sine theta, cosine theta, times, we'll say u1, u2. Is that cool? You guys kind of with me? This is... Alright, I'm doing the exact same stuff we just did. I'm going to apply t to some vector u that's in r squared. And then what am I going to do? Apply t to some vector v that's in r squared. And then I'm going to check to see that if I add them, I get what I would have gotten if I would have applied t to u plus v. I'm trying to show T of u plus T of e equals what I would have gotten if I would have added the vectors first. Yes? So that's where the square root failed, for example. So these transformations don't have to succeed. They could be non-linear. In fact, part of you should feel like, how could this be linear? It's freaking trig shit there. That's not linear. Does anyone know, does anyone remember, this came up very briefly, so if you don't remember, it's okay, but what that matrix does?
It rotates.
Rotates, kick ass, by the angle you pick. Okay. And a really neat question, I might make a bonus question, is to find the eigenvectors for this. Because that connects to e to the I pi plus 1 equals 0, that kind of shit. Real quick question. Do you guys know what this does? Do you guys know what that does?
It's a circle in the complex part.
Yeah, but if you apply it with a specific theta, it'll just rotate. So if I have the vector 1, 0, and I apply e to the I pi, it'll rotate it by pi, which makes it negative 1. Which is trippy as shit. I'm sorry, I'll stop. You're scared. Go. Okay. So I haven't done this yet. What is T of u? It would be, can somebody help me out?
U1 cosine theta.
U1 cosine theta,
Minus U2 sine theta.
U2 sine theta,
U1
sine theta,
plus U2.
plus U2 cosine theta. And then I do that with V, and then I try to show that when I add those together, I get the same thing as I would have if I would have just applied theta u plus V. Are you guys kind of with me? Can you guys see the level of mathematics required? There's not much. But I'm not going to give you a bunch of these because then it just becomes busy. I'm hoping everybody can see how simple that is. Oh my God. It's just never enough time. Can somebody tell me, all right, hopefully that's true. If you want to see the rest of that, let me know. Can somebody tell me anything about this matrix? For any given theta, that matrix has some good properties. In fact, even without that, what's the determinant of that matrix? 1. What is are the columns related to each other in an interesting way? Oh, I see what you're saying. Yeah, I see. Yeah, they're kind of like derivatives across. I see that. What's the dot product of the first column and the second column? 0. Yeah. It'd be negative sine theta cosine theta plus sine theta cosine theta, which is 0. Yes. So they're orthogonal. They're even more than that. They're orthonormal because cosine squared plus sine squared is 1. So each column vector has a length of 1 and it's orthogonal to the other two. So that's an orthonormal freaking matrix strain. Sorry. That's just orthogonal. That'll be alright. No, I won't. Sorry, guys. What was my point? God damn it. Where are you? Oh, here's the neat thing. If our transformation is orthogonal, meaning it's defined based on an orthogonal matrix, then transforming and then taking the dot product. So the transform of x dotted with the transform of y. Are you guys with me? So the transform of x does not have to be x. The transform of y does not have to be y. But the really nifty thing is, if I dot them, I get the same thing as x dot y. Which kind of makes sense. If this rotates through a specific angle and I rotate both vectors, doesn't that preserve the angle between the two vectors? And isn't the angle between the two vectors implicitly defined based on what the value of the dot product is? Yes? So that kind of makes complete sense. That's my hope. Okay. The length. This should also kind of make sense. It preserves the dot product. It preserves the length. And we already know that one. Silly. The preservation of the dot product leads to the preservation of angles. Blah, 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 blah. Okay. That is if T is orthogonal. It does not have to be that matrix we looked at. That is one example of an orthogonal transformation. It's got a matrix that's orthogonal. That's at the heart of its definition. Fudge. It's just an eternal. All right, I'm sorry. Let me pick out what's really important here. Oh, everything's freaking important, Jeff. We don't have time for that. Oh, just to show you a couple examples. Let me see if you guys can tease out what these letters mean. R is obviously, R1, but just to show you an example, I'm sorry, you can't even see what I'm writing. Just to show you some flexibility in how you can define this stuff. So I've defined my transformation. What do you guys think big P means? The space of polynomial functions. So, do you all agree that that interval, if I feed it a polynomial function, it will come out with an element of R1? What does that mean? If I integrate a function with definite limits, I get a freaking scalar or number, yes. You with me? That's all that says. Then the question would become, is it linear? Is it linear? And of course, is integration linear? The integral of the sum is the sum of the integrals. Yes, that's a fundamental property. It's just area, so I can come blah, 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 blah. What'd your teacher tell you today? Blah, 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 blah. I'm sorry. I'm trying to pick and choose here as to what I can do. Oh, that's huge. Oh, shit. We ain't got time for that. Nobody got time for that. Damn it. There's no way I can show you all that. That sucks a lot. I think that's in 8.2. Okay, here's what I'm gonna do. Let me first do this while I'm thinking. Here's the practice file. So next time I'm gonna have the answer key for this thing somehow magically. The next time is freaking Wednesday. We have a two-part final, yes? Because I'm not going to try to cram a whole final into an hour or 20 minutes or whatever. That's part of what I want to talk to you on the day of the review is if you have any strong feelings as to what part 1 should be versus part 2. Because I'm open to... if I were you, I would want part 1 to be more recent stuff. That's one way to break it up. Yes? Or some of you guys look so beat up, you're like, just make it, give it to me. God damn it. Do what you're gonna do, man. Did I give you guys one? Yeah. Okay. So, I really like this. I wish I would have made this the final, but oh well. I made this the practice final, damn it. So now I just gotta make a whole new test. Yay, Jeff. That should look kind of familiar. But I'm making you do a little bit more with it, I think. This should look kind of familiar. But I'm making you do more with it, ha ha ha. So we'll talk more about potential part 1 versus part 2. In the meantime, I'm going to try to make a summary sheet of chapter 8 like I did with chapter 6. Because we went through it pretty quickly. Okay. So I'll see you guys on Wednesday. We're done with new stuff for the semester, by the way, so celebrate however you like.
We got to 8.2, right? Or
We got to 8.2, yes.
Okay.
We sort of just didn't quite do everything in 8.1 and 8.2. Yeah.
For Calc 3, our final's mostly going to be on chapter 16, right?
No, it's going to be cumulative.
Yeah, cumulative.
Oh, I see what you mean.
Yeah. But
It
more-
might be this much heavier, the more recent stuff, yeah.
I was gonna focus on school. Leave out
Oh, what's is LU factorization?
Oh,
I don't see it on the practice.
yeah, that's what I got to be careful. If I put everything on here that could be on there, it would be this big.
Yeah.
So LU could be on there, yeah.
Could be on there.
I didn't even think about it, but at that moment, yeah.
So I'd say to study with us, the practice file is really good, and then look at the practice or the tests.
Is next Monday a holiday?
Yes,
That's Monday's a holiday.
that's why we're like.
Yeah, I was like,
No, unfortunately, no.
yeah.
Oh, you're not even.
Yeah, I'm the.
Is it the same teacher?